In Chapter 2, we learned about subatomic particles and said that electrons are found in a cloud outside the nucleus. In this chapter, we will be getting into more detail about where electrons are in the atom, but first we will talk about energy. We will see a lot of parallels between light and electrons, and we will also find out how light and electrons interact. Electromagnetic energy can be found in waves, which have three main properties: wavelength, represented with the Greek letter lambda, frequency, represented with the Greek letter nu, and amplitude, represented with a capital A. Wavelength is, as the name suggests, how long the wave is. If we measure from the peak of one wave to the peak of the next, that would give us one wavelength. In the figure, the top left wave has a long wavelength, whereas the bottom left wave has a short wavelength. Frequency is how fast the wave travels. It is how often a new wave arrives at a certain point in space. I think of this like trains coming into a subway station. The frequency is how often a new train arrives. The top left wave in the figure has a low frequency, whereas the bottom left wave has a high frequency. The amplitude tells how tall the wave is, but it is not measured from bottom to top. Instead, it is measured from midline to peak or midline to trough. The top right wave has a higher amplitude than the bottom right wave. Wavelength and frequency are related by the equation c equals lambda nu. C is the speed of light, which is a constant, and has the value 3 times 10 to the 8 meters per second. Because c is a constant, as one variable on the other side of the equal sign goes up, the other one must go down. Therefore, wavelength and frequency are inversely proportional. The wave on the top has a long wavelength and low frequency, whereas the wave on the bottom has a short wavelength and a high frequency. As you use this equation, since speed of light is given in meters per second, wavelength must be in meters so that the units match. Frequency is in seconds to the minus 1, which is the same thing as seconds in the denominator, or per second. Another name for per second is hertz. The electromagnetic spectrum includes a large range of wavelengths and frequencies. The visible region is only a small portion of the spectrum. On the right side of this diagram are longer wavelengths, lower frequencies, and lower energies. Just past the red is the infrared. Then the microwave is longer wavelengths, and then radio is the longest, with some radio waves being the length of a whole house. On the left side of the diagram are shorter wavelengths, higher frequencies, and higher energies. Just past the blue is the ultraviolet, then X-ray is shorter wavelengths, then gamma rays have the shortest wavelengths and highest frequencies and energies. We can use the equation c equals lambda nu to solve for either wavelength or frequency. In this example, we are asked to find wavelength of light in nanometers that has a frequency of 7.29 times 10 to the 14 per second. You are given the speed of light, which is 3.00 times 10 to the 8 meters per second. You will not need to memorize it. You do need to memorize equations, like c equals lambda nu. The equations you need to know are listed at the bottom of the study guide for each chapter. First, we would need to rearrange our c equals lambda nu equation to solve for the missing variable, in this case lambda. We need to get lambda by itself on one side of the equal sign. We do that by dividing both sides of the equation by nu, the frequency, and we come out with lambda equals c divided by nu. Rearranging equations is a key skill for this class. Make sure you understand the algebra involved with these rearrangements. Once we have rearranged our equation, we plug in our numbers from the problem. 3.00 times 10 to the 8 meters per second for c, and 7.29 times 10 to the 14 per second for nu. Notice that per second in the numerator cancels out with per second in the denominator, so we end up with meters for our unit of wavelength. We come out with 4.12 times 10 to the minus 7 meters. The problem is actually asking for nanometers, so we have to do a conversion. We start with our 4.12 times 10 to the minus 7 meters, set up a conversion factor with meters on the bottom and nanometers on top, and fill in the prefix that corresponds to nano, 10 to the minus 9 on the bottom of our conversion factor next to meters. Remember, the prefix and the power of 10 go on opposite sides of the conversion factor because they mean the same thing. This tells us that we need to divide by 10 to the minus 9, and we come out with 412 nanometers. What is the frequency of light with a wavelength of 366 nanometers? C is equal to 3 times 10 to the 8 meters per second. Is it A, 8.20 times 10 to the 5 per second, B, 1.09 times 10 to the 20 per second, C, 8.20 times 10 to the minus 4 per second, or D, 8.20 times 10 to the 14 per second? The answer is D, 8.20 times 10 to the 14 per second. First, we convert nanometers into meters by multiplying by 10 to the minus 9. Then we plug into a rearranged form of our C equals lambda nu equation. The rearranged form, which has frequency by itself, is nu equals C divided by lambda. We plug in our speed of light on top and our wavelength in meters on the bottom and come out with D for our answer.